So welcome to module 3 of this course. Now what we're going to be doing in this module is learning the core machine learning algorithms that come with TensorFlow. Now these algorithms are not specific to TensorFlow, but they are used within there, and we'll use some tools from TensorFlow to kind of implement them. But essentially these are the building blocks before moving on to things like neural networks and more advanced machine learning techniques. You really need to understand how these work because they're kind of used in a lot of different techniques and combined together. And what I'm about to show you is actually very powerful if you use it in the right way. A lot of what machine learning actually is, and a lot of machine learning algorithms and implementations in businesses and applications and stuff like that, actually just use pretty basic models, because these models are capable of actually doing, very powerful things. And when you're not dealing with anything that's crazy complicated, you just need some basic machine learning, some basic classification, you can use these kind of fundamental core learning algorithms. Now, the first one we're going to go through is linear regression, but we will cover classification, clustering, and hidden Markov models. And those are kind of going to give us a good spread of the different core algorithms. Now, there is a ton, like thousands of different machine learning algorithms. These are kind of the main categories that you'll cover, but within these categories, there is more specific algorithms that you can get into. I just feel like I need to mention that because I know a lot of you will have maybe seen some different ways of doing things, and this course might show you, a different perspective on that. So let me just quickly talk about how I'm going to go through this. It's very similar to before. I have this notebook, as I've kind of talked about. There is a link in the description. I would recommend that you guys hit that and follow along with what I'm doing and read through the notebook. But I will just be going through the notebook, and then occasionally what I will actually do, I need to open this up here, is go to this kind of untitled tab I have here and write some code in here. It's because most of what I'm going to do is just copy code over into here so we can see it all in kind of one block, and then we'll be good to go. And the last note before we really get into it, and I'm sorry I'm talking a lot, but it is important to make you guys aware of this, you're going to see that we use a lot of complicated syntax throughout this kind of series and the rest of the course in general. I just want to make it extremely clear that you should not have to memorize or even feel obligated to memorize any of the syntax that you see. Everything that you see here, I personally don't even have memorized. There's a lot of what's in here that I can't just come up with on the top of my head. When we're dealing with kind of a library and module so big that like TensorFlow, it's hard to memorize all those different components. So just make sure you understand what's happening, but you don't need to memorize it. If you're ever going to need to use any of these tools, you're going to look them up. You're going to see what it is. You're going to be like, okay, I've used this before. You're going to understand it, and then you can go ahead and copy that code in and use it in whatever way you need to. You don't need to memorize anything that we do here. All right, so let's go ahead and get started with linear regression. So what is linear regression? Well, it's one of the most basic forms of machine learning, and essentially what we try to do is have a linear correspondence between data points. So I'm just going to scroll down here to a good example. So what I've done is used matplotlib just to plot a little graph here, so we can see this one right here. And essentially this is kind of our data set. This is what we'll call our data set. And what we want to do is use linear regression to come up with a model that can give us some good predictions for our data points. So in this instance, maybe what we want to do is, given some X value for a data point, we want to predict the Y value. Now in this case, we can see there is kind of some correspondence linearly for these data points. Now what that means is we can draw something called a line of best fit through these data points that can kind of accurately classify them, if that makes any sense. So I'm going to scroll down here and look at what our line of best fit for this data set actually is. We can see this blue line, it pretty much, it is the perfect line of best fit for this data set. And using this line, we can actually predict future values in our data set. So essentially, linear regression is used when you have data points that correlate in kind of a linear fashion. Now, this is a very basic example because we're doing this in 2 dimensions with X and Y, but oftentimes what you'll have is you'll have data points that have, 8 or 9 kind of input values. So that gives us, a 9-dimensional kind of data set. And what we'll do is predict one of the different values. So in the instance where we were talking about students before, maybe we have a student's, midterm grade and their second midterm grade, and then we want to predict their final grade. What we could do is use linear regression to do that, where our kind of input values are going to be the 2 midterm grades, and the output value is going to be that final grade that we're looking to predict. So if we were to plot that, we would plot that on a 3-dimensional graph, and we would draw a 3-dimensional line that would represent the line of best fit for that data set. Now, for any of you that don't know what line of best fit stands for, it says this is just the definition I got from this website here. Line of best fit refers to a line through a scatter plot of data points that best expresses the relationship between those points. So exactly what I've kind of been trying to explain. When we have data that correlates linearly, and I always butcher that word, what we can do is draw a line through it, and then we can use that line to predict new data points. Because if that line is good, it's a good line of best fit for the data set, then hopefully we would assume that we can just, pick some point, find where it would be on that line, and that'll be kind of our predicted value. So I'm going to go into an example now where I start drawing and going into a little bit of math so we understand how this works on a deeper level, but that should give you a surface level understanding. So actually I'll leave this up because I was messing with this beforehand. This is kind of a data set that I've drawn on here. So we have our X and we have our Y and we have our line of best fit. Now what I want to do is I want to use this line of best fit to predict a new data point. So all these red data points are ones that we've trained our model with. They're information that we gave to the model so that it could create this line of best fit, because essentially all linear regression really does is look at all of these data points and create a line of best fit for them. That's all it does. It's pretty, I don't know the word for it. It's pretty easy to actually do this. This algorithm is not that complicated. It's not that advanced. And that's why we start with it here, because it just makes sense to explain. So I hope that a lot of you would know in 2 dimensions, a line can be defined as follows. So with the equation, y equals mx plus b. Now b stands for the y-intercept, which means somewhere on this line. So essentially where the line starts. So in this instance, our b value is going to be right here. So this is going to be b because that is the y-intercept. So we could say that that's like maybe, we go on, we'll do this. We'll say this is like 1, 2, 3. We might say b is something like 0.4, right? So I could just pencil that in. So 0.4. And then what is mx and y? Well, x and y stand for the coordinates of this data point. So this would have, some x, y value. In this case, we might call it, something like, what do we want to say? 2, 2.7. That might be the value of this data point. So that's our x and y. And then our m stands for the slope, which is probably the most important part. Now, slope simply defines the steepness of this line of best fit that we've done here. Now, the way we calculate slope is using rise over run. Now, rise over run essentially just means how much we went up versus how much we went across. So if you want to calculate the slope of a line, what you can actually do is just draw a triangle. So a right angled triangle anywhere on the line. So just pick 2 data points. And what you can do is calculate this distance and this distance, and then you can simply divide the distance up by the distance across, and that gives you the slope. Now, I'm not going to go too far into slope because I feel like you guys probably understand what that is, but let's just pick some values for this line, and I want to actually show you some real examples of math and how we're going to do this. So let's say that our linear regression algorithm, comes up with this line. I'm not going to discuss really how it does that, although it just pretty much looks at all these data points and finds a line that, it splits these data points evenly. So essentially, you want to be as close to every data point as possible, and you want to have as many data points, you want to have like the same amount of data points on the left side and the right side of the line. So in this example, we have, a data point on the left, a data point on the left. We have 2 that are pretty much on the line, and then we have 2 that are on the right. So this is a pretty good line of best fit because all of the points are very close to the line and they split them evenly. So that's kind of how you come up with the line of best fit. So let's say that the equation for this line is something like y equals, let's just give it 1.5 and x plus, and let's say that value is just 0.5 to make it easy. So this is going to be the equation of our line. Now notice that x and y don't have a value. That's because we need to give the value to come up with one of the other ones. So what we can do is we can say if we have either the y value or we have the x value of some point, and we want to figure out, where it is on the line, what we can do is just feed one in, do a calculation, and that will actually give us the other value. So in this instance, let's say that, I'm trying to predict something and I'm given the fact that x equals 2. I know that x equals 2, and I want to figure out what y would be if x equals 2. Well, I can use this line to do so. So what I would do is I'm going to say y equals 1.5 times 2 plus 0.5. Now, all of you quick math majors out there, give me the value of 3.5, which means that if x was at 2, then I would have my data point as a prediction here on this line. And I would say, okay, so if you're telling me x is 2, my prediction is that y is going to be equal to 3.5 because given the line of best fit for this data set, that's where this point will lie on that line. So I hope that makes sense. You can actually do this the reverse way as well. So if I'm just given some y value, so say I know that, my y value is at like 2.7 or something, I could plug that in, just rearrange the numbers in this equation and then solve for x. Now, obviously, this is a very basic example because we're just doing all of this in 2 dimensions, but you can do this in higher dimensions as well. So actually, most times what's going to end up happening is you're going to have, like 8 or 9 input variables, and then you're going to have one output variable that you're predicting. Now, so long as our data points are correlated linearly in 3 dimensions, we can still do this. So I'm going to attempt to show you this actually in 3 dimensions just to hopefully clear some things up, because it is important to kind of get a grasp and perspective of the different dimensions. So let's say we have a bunch of data points that are kind of like this. Now I'm trying my best to kind of draw them in some linear fashion using like all the dimensions here. But it is hard because drawing in 3 dimensions on a 2-dimensional screen is not easy. Okay, so let's say this is kind of like what our data points look like. Now I would say that these correlate linearly like pretty well. They kind of go up in one fashion, and we don't know the scale of this, so this is probably fine. So the line of best fit for this data set, and I'll just put my kind of thickness up, might be something like this, right? Now notice that this line is in 3 dimensions, right? This is going to cross our, I guess this is our X, Y, and Z axes. So we have a 3-dimensional line. Now the equation for this line is a little bit more complicated. I'm not going to talk about exactly what it is, but essentially what we do is we make this line and then we say, okay, what value do I want to predict? Do I want to predict Y, X, or Z? Now, so long as I have 2 values, so 2 values, I can always predict the other one. So if I have, the X, Y of a data point, that will give me the Z. And if I have the Z, Y, that will give me the X. So long as you have, all of the data points except one, you can always find what that point is based on the fact that, we have this line and we're using that to predict. So I think I'm going to leave it at that for the explanation. I hope that makes sense. Again, just understand that we use linear regression when our data points are correlated linearly. Now, some good examples of linear regression were, that kind of student predicting the grade kind of thing. You would assume that if someone has, a low grade, then they would finish with a lower grade. And you would assume if they have a higher grade, they would finish with a higher grade. Now, you could also do something like predicting, future life expectancy. Now, this is kind of a darker example, but essentially what you could think of here is if someone is older, they are expected to live, like not as long. Or you could look at health conditions. If someone is in critical illness condition, they have a critical illness, then chances are their life expectancy is lower. So that's an example of something that is correlated linearly. Essentially, something goes up and something goes down, or something goes up, the other thing goes up. That's kind of what you need to think of when you think of a linear correlation. Now, the magnitude of that correlation, so how much does one go up versus how much one goes down, is exactly what our algorithm figures out for us. We just need to know to pick linear regression when we think things are going to be correlated in that sense. Okay, so that is enough of the explanation of linear regression. Now we're going to get into actually coding and creating a model, but we first need to talk about the data set that we're going to use in the example we're going to kind of illustrate linear regression with. Okay, so I'm here and I'm back in the notebook. Now these are the imports we need to start with to actually start programming and getting some stuff done. Now the first thing we need to do is actually install sklearn. Now, even if you're in a notebook, you actually need to do this because for some reason it doesn't come by default with the notebook. So to do this, we just did an exclamation point, pip install -q sklearn. Now, if you're going to be working on your own machine, again, you can use pip to install this, and I'm assuming that you know to use pip if you're going to be going along in that direction. Now, as before, since we're in the notebook, we need to define, we're going to use TensorFlow version 2.x. So to do that, we're going to just, do that up here with the %sign, and then we have all of these imports, which we're going to be using throughout here. So from, future, import, absolute import, division, print function, Unicode literals, and then obviously the big ones, so NumPy, pandas, matplotlib. We're going to be using IPython. We're going to be using TensorFlow. And yeah, so I'm actually just going to explain what some of these modules are because I feel like some of you may actually not know. NumPy is essentially a very optimized version of arrays in Python. So what this allows us to do is lots of kind of multi-dimensional calculations. So essentially, if you have a multi-dimensional array, which we've talked about before, right, when we had, those crazy shapes like 5, 5, 5, 5, NumPy allows us to represent data in that form and then very quickly manipulate and perform operations on it. So we can do things like cross product, dot product, matrix addition, matrix subtraction, element-wise addition, subtraction, vector operations. That's what this does for us. It's pretty complex, but we're going to be using it a fair amount. Pandas. Now, what Pandas does is it's kind of a data analytics tool, I almost want to say. I don't know the formal definition of what Pandas is, but it allows us to very easily manipulate data. So, load in data sets, view data sets, cut off specific columns or cut out rows from our data sets, visualize the data sets. That's what Pandas does for us. Now, Matplotlib is actually a visualization of kind of graphs and charts. So we'll use that a little bit lower when I actually graph some different aspects of our data set. The IPython display, this is just specific for this notebook. It's just to clear the output. There's nothing crazy with that. And then obviously we know what TensorFlow is. This crazy import for TensorFlow here, so compat v2 feature column as FC, we'll talk about later, but we need something called a feature column when we create a linear regression algorithm or model in TensorFlow, so we're going to use that.